So in this video, I'm going to introduce you electric field. Electric field is, I think that's one of the most interesting things in physics, that we cannot really directly feel the electric field or field in general. We don't really directly feel the field, but we say it around us. And here I'm going to define what electric field is, and also introduce you how we can, if we can't feel it, if we cannot directly measure, what does it mean by electric field, and how do we measure? How do we say what it is? So that's what I'm going to introduce you. Um, let's see. Electric field. Electric field. It's not something we feel it directly. You know, like a speed, inertia, force, we can directly measure. We can't really directly measure the electric field, but what can we measure? Force, we can measure. So we use this, right, to measure force. It has a spring inside. If it's pushed or pulled, we can so we can measure this. This is the device to measure force. We can either push or pull, right? And it has a spring inside. So we use this kind of a device to measure force. Electric force. We use Coulomb's law. That is the force between two charges. So I could have a, let's say, big Q. And then here is the little q, right? Coulomb's law say there's a constant, Coulomb constant, 9.0 times 10 to the 11, right? 9.0 times 10 to the 11 Newton meter square divided by Coulomb square times big Q, little q divided by d squared, the product of the two charges and this. So that's the force, let's say the force on Q, the force on little q. So the force on the little q, is the same thing as the force on the big Q. So we can kind of see that, let's say this little q is in the environment of a big Q. Earth and apple, we've been saying apple, here is a Swiss cheese. So let's say apple and a Swiss cheese, right? Apple falls, cheese falls because of gravitational force that's between them. We say the force is exerted on the cheese is the same as exerted on the earth, but we can imagine that Earth is here. And Earth has an environment. And then when the cheese came over, they both feel the force. And then the cheese was introduced into the environment of our Earth. It could be cheese and the tomato, and depends on the masses. So there's a Earth, the mass of the Earth, and then depends on the tomato's mass or the cheese mass or the apple, they have a different gravitational force. Also Vinasha, right? This or this. But either way, there's a big Earth that's making the environment. Similarly, this is the Q. There's a big Q. And then the little q comes over, and this little q feels the force. This is the little q. This little q feels the force, and then I have this spring scale, and then I can measure. It's going to be positive, and it's going to be repulsive. So it's going to push it this way, repel it, and then I can measure the force. I can measure the force here. What if I bring this little q farther away? The force becomes a little bit less by 1 over d squared. Force gets stronger. So just like this, I have a big Q and the little q comes over. And the environment that I said that's created by this big Q is we define as an electric field. So this electric field is being created by this big Q. So then here is so I say the little q is in the environment electric field created by this big Q. So the definition of electric field, so electric field is also a vector, just like a force. It's force divided by this little q per unit charge, so this little q. So that's it becomes Newton per Coulomb. There's no new unit. This is the definition of an electric field. It's the force per charge. Electric field is a force per charge, right? That's been created by BQ. So what I've been saying here is, let's see, again, force always happens in between the two charges. So I have a big Q here, some kind of a Q, and then this is this little thing, we call it as a test charge. It's a known charge Q that you put it on your device, let's say. And we typically use the positive charge so that it's easier to convert. So then if we have two charges, it's going to feel the force. We can measure. This by itself, there's no force. It's only field that's created by this Q. We can't measure unless we bring it. Then we can measure. So what I do is I bring this little test charge, and here's, let's say, imagine like there's like a little stick here. Little stick here. and spring. It's connected with a little spring. So then when I bring this little Q in an environment of a little big Q, electric field generated by this Q, it's going to feel force. So let's say, okay, electric force on this little one is pointing in this way, Fe, right? About this much. What if I bring this little Q here? The force will be stronger. And again, it's going to be pointing, right? It's always the force is going to be extension of the between the two charges. So it's going to be like this. So this is going to be like this, away from each other, bigger. So if I bring it here, it's going to be over here, over here. It's going to be like this. So you can kind of draw forces. If you were to bring it over there, how much forces is it going to feel? And what I drew here, the arms, this is called electric field lines. So this electric field line is there without the little q. This generates this electric field just being there. In this case, if it's a point charge, if Q is a point charge, then electric field is going to be, electric field is going to be KEQ over D square. So electric field will be stronger here, weaker here, but it's going to be everywhere, coming out radially outward. Positive, radially outward, right? Because if you bring that little test charge, it's going to be repelled. So it's going to be all around. And then if it's negative, radially inward. Do you see it? So you bring this little charge here and then measure the force, but without it. So you can imagine there's going to be an electric field line. So if you bring it, you feel the force. Bring it, feel the force. And this green line is there. This electric field line is there without the little test charge. Just it's been created by this one charge. So as long as you have an existence of a charge, you could have a field created. And that's what the electric field is. And this green line is the electric field lines that once you bring the test charge, that's where the force, the direction of a force would be. The magnitude of the force is going to be depends on magnitude of a test charge and the big Q. So electric field lines are the to show the direction. So electric field lines, I'm going to rewrite it here. Electric field lines represents the direction, and also the magnitude of electric field. So direction is by the arrowhead. The arrowhead. It's also the same as the direction of force with a positive test charge. Again, this little charge is called a test charge. The little one. This little one is the test charge. That's typically we use a positive one. It's easier that way. And then a denser line region it has a stronger field, and less dense line region is a weaker electric field. So unlike vectors we were saying is that you make if it's a bigger magnitude, you make it longer. This is not about the length, because electric field lines never going to be discontinued. Electric field line never disconnected. That means that you can represent with the length of that line. Like remember the force, electric force never becomes zero. It approaches to zero by d squared, 1 over d squared, but it never becomes zero. So electric field lines never get disconnected either. So we can't really use that length of the arrow to represent the magnitude of electric field lines. So instead we represent with the density. How dense? Less dense. So here, we have a positive Q. So I can, let's do it again. This is the big Q, right? And then if I bring the little test charge here, it's going to be in this direction. So all this electric field line is coming out radially outward from this big Q. And as you can see, the closer to the big Q, you're going to have a more field line penetrating per unit area. The farther away, you're going to have a less field line penetrating per unit area. So you can see the farther you go away, electric field gets less. Similarly, that means that if you bring this one here, the force gets weaker and weaker, right? So this is the electric field line of plus Q. How would you write, if that's the case, if you have a 2Q plus 2Q now? How would you write the electric field lines of a positive 2Q? Try it. So here we have a positive Q. We have 1, 2, 3, 4, 5, 6, 7, 8. I drew 8 field lines just for symbol of plus Q. So for plus 2Q, I'm going to write it was 8, and then now the charge is doubled. Charges become double 2Q now, and then the same test charge, it's going to be double the field lines. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, maybe 16. So 16 lines, 8 lines, 16. Not that length, it's that. Okay, so this is the electric field lines of a 2Q. If the plus Q is 8 lines, let's say, that represents the more dense lines, right? And then still it's the same, radially outward. How does the minus Q charge will look like? What kind of electric field line does the minus Q have? So it's moved from Q to plus Q to minus Q. So if I were to bring the minus Q here, the direction of a force is going to be attracted, plus test charge to minus test charge. So it's going to be coming towards minus Q. And the strength of an electric field of minus Q should be the similar thing as the plus Q. So I'm going to draw the same amount of line, same number of line as the plus Q, but change this to be inward. Because if you bring the test charge, it's going to be, force is going to be this way. If you bring the little test charge, right, it's going to be that way. So you draw all these lines as if you bring that little test charge. You just bring the little test charge and which direction it's going to be pulled in. That's going to be radially. All right. Can you write plus Q minus Q? This is called electric dipole. So now instead of a point charge, we have a set of two charges. And then I bring a little test charge here, right? How about the electric field that's created by these two plus and minus Q electric dipole charge? Can you draw the electric field lines of that? Can you? How about this? This is going to be hard. Plus, 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 plus. This is called capacitor, that you have a positively charged, negatively charged plate. Same amount of charges, but let's say it's on a flat plane. How about electric field lines created by these two configuration of the charges? All right, so let's see, try these, and then I will, if I have time, I'll do this in the class. All right, see you.